This meeting is being recorded.
So welcome to today's seminar where we will see presentation of Jocelyn Thiebaut about sparse elements and generalizations. Please.
So the goal of this talk is to give you a brief, but I believe complete introduction of what is sparse elements, because we never heard about it. So I won't come with the definition to start with, but first of all this talk is based on 3 different papers. The 2 first are done with Stéphane Pessi and Mahan Boucher in the context of multiplication. And the last one we submitted recently, and it's joint work with Luca Iselman, Tom Davo, Luca Iselman, and Sanjay Stradler. So let's do it. So just the basis tournament. It's the annotation of the complete graph. So this is an example, and a way of showing tournaments is to give an order on the vertices. Here we put back the arcs, and usually what we do is we only depict backward arcs that are arcs that go from right to left. So as you can see, depending on the order we choose from the beginning, the representation change. And this is what will interest us. So now sparse tournaments. It seems like a bit weird to say sparse tournaments because tournaments are by definition not sparse. But just to give you an intuition, one is sparse and the other one is not. And the definition we give is that a tournament is sparse if it admits an ordering such that the backward arcs form a matching. So as you can see, the first one is sparse and not the second one. In fact, it's not the proof that this is not sparse because we just need to admit one ordering. This is just one of many orderings possible. But there is a way to see that this can't be sparse. There's someone has an intuition, like one small argument that this can't be sparse. We look at the minimum in degree of this graph, and it's not hard to see that every vertex has at least 2 in neighbors, and therefore there is no way that the first vertex does not have 2 backward arcs coming into them. So now let's try to see how we can compute a sparse ordering. It can be done in Polynomial time, and in fact, most of the intuition the algorithm will find will be based on how does it work in a cyclic tournament. And in a cyclic tournament, there is a particular ordering called topological ordering, where there is no backward arc. And the way to compute a topological ordering is to just look for the vertex of in degree 0, put it at the end of the ordering, remove from the graph, and repeat. And if at some point we don't find a vertex of in degree 0, then we know it's not a cyclic. And the idea for sparse tournaments would be roughly the same. That is, if we have a vertex of in degree 0, we put it at the end. If, this is what I said earlier, we have the smallest in degree of the graph is greater than 2, then we know it can't be sparse. But in between, we have to be a bit more careful how to position the vertices of the in degree 1 and how to remove them, and also repeat, but being sure not to forget that we remove a backward arc. And here in this process, we may return false if we have we find a configuration that makes the tournament not sparse. This was just to give you a rough idea of how the algorithm works. I'm not going too much into details for this part. So we first studied sparse tournaments in the context of cycle packings. So first, let's try to see what's the vertex-disjoint cycle packing in tournaments. So you have a tournament and you just want to find vertex-disjoint cycles and of the maximum size. And it's well known that in tournaments, it's enough to look for triangles. So the packing cycles is the same that packing triangles. So for example, this is a maximum packing of cycles. And it's packing cycles is a fundamental problem in graph theory. And we have many results that are both structural and algorithmic. But unfortunately, on tournaments, we have some structural results, but from the algorithmic point of view, we don't have much. Another reason to focus on cycle packing is that there are it's the dual of feedback sets in tournaments, which we'll talk about those more in detail later. But basically, just to define the problems, you have a tournament and you want to find a minimum set of vertices or of arc, such that when you remove them from the graph, you make it cyclic. So this is the minimum feedback vertex set, and this is the minimum feedback arc set if I didn't do any mistake, which is not impossible. So there is many results. I just showed you I believe the best one known so far on those two problems. And as I said, there are the link between packing cycles and feedback sets they are dual, one from each other. So most of the algorithmic results we can find from a vertex cycle packing in tournaments come from free-set packing. So this is just an extension of what the free-set packing results. But as you can see, the main part was unknown, namely if it was NP complete or polynomial, and it turns out it's NP complete. And I will just show you the idea of the proof. So we come from max2 sats, a special case of max2 sats, where each variable appears once negatively and twice positively, at most twice positively. Sorry, it's not the same. Otherwise, it's polynomial. And we want an destination that satisfies a maximum number of closes. So an example. So here, x1 appears once positively and once negatively. x2 appears twice positively and once negatively, and so on. Okay, how does the reduction work? So we'll have, as usual, variable gadgets, and this is for each variable we'll construct these tournaments. Note that it's not sparse, but we'll make it sparse in the second part. So what's interesting with this tournament is that there are at most 3 triangles, vertex-disjoint triangles, because there are 11 vertices, so it's not possible to do more. And we'll focus on 2 specific packings on those on this tournament, namely this one that I would call delta true. The packing itself is not important. What's important is that it leaves x and x prime free. And on the other direction, we have also this packing, which has 3 triangle and leaves those 2 vertices free. And for each clause, we'll have these small tournaments of 2 vertices. And now how do we link those variables gadgets and close gadgets together? Well, it's pretty straightforward. So if, like for example, C1 is x1 or x2, and if a variable appears positively for the first time, we connect it to x1. But if it appears for the second time, like this, it's the second time the variable appears positively, we connect it to x prime, and we do the same for the negative occurrences, the negative occurrence. And now we'll quickly show you this claim that if there is an assignment that satisfies k clauses, then we can pack at least 3n plus k triangles. So what we'll do is that when you have your assignment, let's say that x1 is set to true and the other variable is set to false, we'll pack delta true when the variable is set to true and delta false when the variable is set to false. And we know that inside we have already free n triangles because every variable gadget contains three triangles. And now what we'll do is that we will have those two vertices free, and we can finish to create one triangles per each clause that is satisfied. This is the easy part of the proof, of course. The other part is not that difficult. You just have to look more in detail and have more structure. But in the end, we can prove the other direction and then complete the proof. So we have also, so what we claimed the focus of this talk was sparse elements. And in fact, you can, as I said, extend this result for sparse. Mainly, you have to kill those vertices. And in fact, it's not that hard. You just have to replace them with this sub-tournament here. And the idea of this was you can't take this vertex in more than one triangle. And here, there will be a triangle that you can do inner, inner triangle in the sub-tournament we added. And then it will leave just one vertex free to use it outside the small sub-tournament. And you do this for all the vertices that need it. And in the end, you can extend easily the proof for sparse tournaments. And in fact, it's also NP-hard to compute feedback vertex set on sparse tournaments. And here, I won't enter into details. It's just a reduction from vertex cover. So now we talked about vertex-disjoint cycles in tournaments. Now we'll talk about arc-disjoint cycles in tournaments. And it turns out it's not exactly the same scenario. That is, if you ask to pack as much triangles in this tournament, you'll find 2. But if you want to pack as many cycles in this tournament, you'll find 3. So unlike the vertex case, it's not the same problem. We have 2 distinct problems, that is packing triangles, packing cycles. And of course, since it's a dual, you still have the number of cycles is still less than the feedback arc set. Obviously, I mean, it's not surprising that both of those problems are NP complete. But in fact, on sparse tournaments, unlike the vertex case, they can be solved in polynomial time. And in fact, you can even say even more, that is, the value in that case is the same. So now, before going into the next part, we have to talk about what we call U tournaments and about patterns. So UN, the tournament, we define the tournament UN as this tournament here. Another way to see this tournament is to consider an acyclic graph and where we reversed its Hamiltonian path. And those tournaments these are 2 examples. Was pretty obvious. But what's interesting with those tournaments is they have specific patterns. What we call pattern is a subsequence of an ordering. And what's interesting with those are those 2 orderings, because there are only 2. But what's interesting is that in the odd case, we have these 2 orderings. These 2 orderings are particular because, especially this one, and this is what we call forbidden pattern. It's forbidden because we can find another ordering of those vertices that is strictly better because we leave 2 vertices free. The U tournaments appears in the hidden algorithm. The part are hid in the algorithm to compute a sparse ordering. And what's interesting is this statement. That is, if a tournament T admits a sparse ordering without forbidden patterns, then the set of backward arcs is a minimum feedback arc set. And we can see a bit the reason why those tournaments are the problem is that here I depicted the feedback arc set of this tournament here, and in fact it's exactly this one. I mean, if you look at those arcs, V3, V2, it's here, V5, V4, it's here, and so on. My point here is that those forbidden patterns, and specifically here, this one, those forbidden patterns are the biggest tournaments that such that the set of backward arcs is not a minimum feedback arc set. And we'll try to prove this. So first, what we'll do is that we take our tournament and we will order the set of backward arcs defined by our ordering according to the head of the arcs. And we take any feedback arc set of the tournament. And our goal is to build a function from this set of backward arcs to our feedback arc set and prove that this function is injective. So to do this, first, you can notice that there is a vertex xi between vi and ui, because otherwise those two vertices are consecutive. And in fact, this is a forbidden pattern in the case where there is only two vertices. So it means that there is a vertex here, and therefore there is a triangle that we need to break. And the feedback arc set had to break at some point. So if this arc, if the backward arc is in the feedback arc set, then we assign this this backward arc to itself by the function. Another case is that this is not in F, but this arc here is in F. And in that case, we consider that we assign the backward arc UIVI to this arc here in red. Now, a little bit more complicated. So we're the case where none of those two arcs are in the feedback arc set. And this one, written very formally, but this one have never been assigned before in any other. There's no other backward arcs such that the function assigned this backward arc to this arc to the backward arc. So if this arc never been assigned before, then we'll take it. And finally, in the last case, we consider the vertex yi, which is just after xi, and we'll prove that this vertex must exist. And since we have a triangle between those three vertices, one of those three arcs has to be taken, not this one. So one of those two. And we take the one that is taken. We assign this backward arc to the one that is taken in the solution. So there are two things to prove here. First, that this vertex is well defined, because if we consider the vertex after xy, it could be technically ui, and in that case there is no triangle, so it's not well defined. And the second thing is that we have to prove that the function is injective. So let's start with the first thing. Suppose that there is no vertex after xy. One thing we can notice is that since we are in the case D, then it means that this arc is not in the solution, this arc is not in the solution, so it means that this last arc here is in the feedback arc set. And furthermore, there is, since we're in the there is an arc before that was assigned to this arc. So we're in this situation here, and now this arc that has been assigned before, the question is in which of those cases it has been assigned. Well, it's a forward arc, so it can't have been taken in case number A, case A. So it's not possible. Let's consider the case B. If it's case B, then it means that this arc has been taken here, and there is no vertex here, no vertex here, no vertex here. And in that case, it's exactly the forbidden pattern for U4. Now, it can't be on case C, because it means that there would be another backward arc landing on BI, and therefore it would not be sparse. And the case D, there are two possibilities. Either it's this arc or this arc. This arc is not possible for the exact same reason. It would be implied that it's not sparse. And this case here is technically possible. But then it would mean that we're in that case where every time there is no vertices between those two vertices. So we're in that case. But now the question is, in which of those cases did we assign this arc? And then we could repeat the argument. It can't be from a backward arc. It could be from a case B, but then we'll have the forbidden pattern for U6, sorry, this time. It can't be C. It could be D, but then we could repeat again, until we arrive to a case B, and therefore we have a forbidden pattern. So it proves that there is the yi, and then the function is well defined. So this was the first part. Now the second part is that the function is injected. So let's take an arc from the feedback arc set, and we want to prove that we assign at most one arc to this arc. So consider first the case where ST is a backward arc. Well, in that case, it necessarily comes from the case A here, and it's easy to see that it's not possible that this arc has been assigned again. So we could. The trickier part is if ST is a forward arc, but we can say several things here. For any backward arcs that has been assigned to ST, we have either S is I'm lost. Okay, yes. So here, either S has been assigned. ST is this vertex here. S is intersects here, and then T is either X, Y here or Y, I here, or it's the opposite in case B and D. That is, T is this vertex here or here, so T is UI, and then S is either X or Y. So it means that we're in this situation, and it's easy to see that you can't have, in that case, because of this, you can't have more than two backward arcs that have been assigned to ST. Because, as I said, S has to be the first, S and T has to be the first or the last vertex, the head or the tail of the arc. So we're in this situation. Now there are several possibilities. So we have this backward arc UI VI and UJ VJ. So now either this comes from case B or D. So it means that S is, I'm just redoing this in more detail. So it means that S is XI or YI, or here we're in case C or D, and then in that case T is XJ or YJ. And now we just have to go through all the possibilities and prove that it's not possible. We'll just do the case C, and in fact, it's not that hard, the case C. So in that case, so it means that T is also UI and also XJ. And in that case, it means it's not possible because it means that this arc has been assigned here in case C, but in case C, we said that this arc must have never been touched before, which is not possible because it has been assigned before when we were considering the backward arc UI VI. So it's not possible. The case D is a bit more complicated, and we have to look a bit more in detail, but the proof is done in a similar way. So let's sum up here. So we have a tournament, and we proved that if it admits sparse ordering without forbidden patterns, then we can just take the set of backward arcs, and it will be a minimum feedback arc set. Now, the good news is that, in fact, it's possible for sparse tournaments to construct in cubic time an ordering without forbidden patterns. And this, the rough idea is that it works well because it has to be patterns are consecutive vertices. So we're not looking for a subgraph or anything. We're looking for consecutive vertices. And the second key that why it's working is that there is only two possible patterns for sparse orderings for U tournaments. But now, combining those two things, it proves that we can compute a minimum feedback arc set on sparse tournaments in polynomial time. So let's just sum up a bit the thing. So these are several results. I guess we'll just focus on those two columns that are for those 2 points here, this one, for sparse tournaments here. I presented you most of the results already. The two I didn't mention are this. So the prime is still APXR, but we can provide an approximation with this ratio, S being the minimum, the mean span of the tournament, which is better than this ratio when S is large. And we can also find a linear triangle for vertex-disjoint triangles in sparse tournaments. So there is also the results on feedback. So I didn't show here for the sake of clarity. Now let's just try to generalize the concept of sparse. How would you generalize this? Then I will start with a small reminder of what cut width is. So you take your tournament, an ordering of the tournament, and the cut width says you look at between two vertices of your orderings, two consecutive vertices of your ordering, and you look at how many backward arcs are going through this cut here. So in that case, it's 1, and you do this for all the possible prefix of your ordering, and you take the maximum value. This would be the width of this ordering, and in that case, it's 4. But of course, depending of the ordering of the vertices, this is the same tournament, just another ordering. You could have a different value, and the cut width of your tournament would be the minimum value among all the orderings of the width of the tournament. Well, the generation of sparse tournaments that we call the parameter that would generate the idea of sparse tournaments, we call degree width, works a bit in a similar way, but instead of focusing between two vertices, we'll focus from the vertex point of view. You could say that like this. So here you take the ordering and you compute how many backward arcs are incident to this vertex. Here it's 1, and you do this for all the vertices. And here the maximum value of this, the maximum value would be the degree width of this ordering. And similarly as before, depending of the order of your vertices, you may have different values, and you want the minimum value. Let's now see the link between the cut width and the degree width. So let's take the ordering that minimize the cut width. So the ordering that is optimal for cut width. Well, If you consider any vertex, you know that at most the number of backward arcs that will come from the right is less than cut widths. And similarly, the maximum number of backward arcs that will go to the left is less than cut widths. So it means that in this ordering, you know that the degrees of this ordering optimal for cut widths is less than 2 times the cut width. And therefore, since the degree is the minimum among all the orderings, it means that degree is less than cut width. And we can't do the same thing on the other side because we can construct tournaments with small degrees but large cut width. Here is an example. This ordering is optimal for cut widths because in tournaments, cut widths can be computed just by sorting the vertices by increasing the degree, and we'll come back on this a bit later. So here, this in the vertices, it's the in degree, so it's sorted by increasing the degree, and you have a cut width of 3, but the tournament have degree width 1, and you could just construct another example with more vertices with the same idea. Another parameter we could link degrees to is feedback vertex set. This is the definition I gave you, but an equivalent definition would be to find an ordering of the vertices that minimize the number of backward arcs. And in fact, this allows you to say that the degrees is less than feedback vertex set, because if you take this the optimal ordering, you know that every vertex will be incident to at most feedback arcs set of the tournament, backward arcs, and therefore the degrees is less than the feedback arc set. And similarly, you can construct tournaments with low degrees but large feedback arc set. Here is an example. You have to kill all the triangles here, so you could repeat this as many times as you want, but the degrees is 1. For feedback vertex set, this is also an example of tournaments with small degrees but large feedback vertex set, because similarly you have to kill all the triangles. Before it was by taking those arcs, and here it just by taking the vertex. And on the other direction, we can also create a tournament with large degrees but small feedback vertex set. Here, it's an example of an acyclic tournament that n plus 1 vertex that is seen by half, sees half of the tournament and is seen by the other half. It's not the optimal ordering for degrees, here it is, but it's still an example where you can build this with the large degrees but small feedback vertex set. So those two parameters are not comparable. Sorry. The idea of degrees, I believe, is, I should have changed this, is the more I think about it, I wanted to say that it's the measure of the acyclicity, if it means anything, of the tournament, but it's more, I believe it would be more correct to say that it's a measure, I believe it's a measure of how far the tournament is from a topological order, which is exactly the same, that saying it's the cyclic, but the small difference in how you say it, I guess, give a better intuition of how I think degrees would work. So how does it work? Then for degrees 0, it's exactly a cyclic tournament. For degrees 1, then it's exactly sparse. And in fact, we can prove that degrees, if the tournament is regular, so it means that for every vertex, the in degree equals the half degree equals half of the graph, basically. Then they have degrees n/2. The side note here is that then maybe there's it's not only regulars. Here it's cyclic equal, degree 0, sparse is more or less equals degrees 1. Technically, the definition also includes degree 0, but it's just a detail. Here, regular, you may have other terms. Of course, I mean, it's not very surprising, but it's NP hard to compute degrees on the determinants. But in fact, there is a way to have a decent approximation algorithm. And in fact, just sorting the vertices by increasing the degree is a free approximation of degree. And it's not very surprising because for two reasons. The first reason is that it's a good, it works for cut widths and it has some similarities with cut widths. But mainly, the main reason is that when you want to compute a topological order, another way of doing this is just to sorter the vertices by increasing the degree. So it gives an intuition that it kind of works how the same way than topological order. And in fact, this ratio is tight. So this is an example of a tournament where the vertices are sorted by increasing in degree. So inside the node, it's the in degree. And here you can find that this vertex is, this ordering has degrees 3, while the optimal is sparse. So you could say here it's also ordered by increasing in degree, which is true, but it's possible to build another example a bit more intricate, a bit more complicated, where here the optimal is not sorted by increasing in degree. And finally, so dominating set, which is known has to be in w.r.t on tournaments, is FPT with respect to degrees. And yeah, okay, let's finish with some open questions. First, is there a better FPT algorithm for free set packing? I guess it's very likely that you can use the sparse property to make a better algorithm than the free and so on to decay. I believe it's doable. And similarly here, if you look at this algorithm is, I'd say, pretty stupid. And even in this example here, you can see that there are lots of vertices of degree 4, and maybe by ordering those vertices in a better way, namely put this vertex here, it would dramatically improve the degrees of the tournament. So maybe by being a bit more clever by sorting the vertices, there is a way to have a better ratio. Okay, so we found a polynomial algorithm for sparse modes. And would it be possible to have an FPT algorithm to compute an optimal ordering? My intuition on this, I guess it's doable. And similarly, can fast be FPT with respect to the degrees? And more general, can other problem can be FPT with respect to degrees? And another even broader question is that these parameters defined for tournaments, we could try to find a way to define it for general digraphs. Cut width is defined for general digraphs. Would it be interesting, or is it just interesting for tournaments? Well, thank you.
Question.
Yes.
First, a simple question. You said it's based on 3 papers, so these are already published, or?
Oh yeah, that's the interesting thing. I forgot to mention. So 2 are published. One is from 2017, I believe. One 2019. But the last one was submitted. So all the results where it's labeled with Tom Mika Iselman and Sanjukta Roy may be false because it hasn't been formally peer-reviewed. I hope I didn't say stupid things, but yeah, technically it's important to mention it.
So is it available on archive or?
No, because the submission is anonymous, so I'm not sure we're allowed to put it on archive. I'm allowed to do this talk. I checked the thing, but technically, yeah, it will be at some point. Yes.
At some point you mentioned you have linear vertex kernel or?
Yes. It's linear kernel is for feedback, vertex-disjoint triangles in Sparse.
Yes. Is there a chance to have sublinear kernel, or is that excluded?
Okay, this result comes from a paper in 2017. So I guess it was just color coding thing. It wasn't tricky. It was pretty straightforward. So it probably has plenty of room for improvement, at least considering the amount of time we put on it for this result. So maybe it's not impossible.
Other questions?
Maybe I'm stupid, but Hamiltonian cycle is easier for tournaments.
Hamiltonian cycle. The first thing is that if it's strongly connected, there is an Hamiltonian cycle, and it's an equivalence. So
Okay, yeah.
So yeah.
But then still TSP doesn't have Okay.
Other questions? Right, so let's thank the speaker again.